let's look at this first question here. We want the antiderivative of 2 cosine t minus t to the fourth plus 1 over t plus 5 over the quantity 1 plus t squared. So just a few things. These should be pretty straightforward. This is going to be a natural log. This is going to be an inverse tan. So just to kind of scan that and show you what each one is. So I'm going to do the first two right away. So this is going to be 2 sine t minus t to the fifth over 5 plus natural log of t in absolute values. And then now let's look at this last one. I'm going to factor out the 5, and I'm integrating 1 over 1 plus t squared dt. I just want to go over how we get the inverse tan one. So remember the inverse, you can look at your notes for the inverse tan pattern, but this tells us we have an a of equal to 1, and we have a u equal to t. So we should have then 2 sine t minus t5, t to the fifth over 5, plus natural log absolute value of t, plus, 5 times 1 over a, which is 1 over 1, and then inverse tan u over a, which is going to be t over 1. So I'm just going to put inverse tan t plus c. Okay, so the next one, next one we can see is a u sub. We have a function and its derivative, a form of the derivative right here. So we're going to have u equal 1 plus x squared. That means du dx equals 2x. And when we solve that for dx, we get dx equals du over 2x. So when we do those substitutions, we're going to put in this substitution here, and we're going to put in this substitution here, that x is going to stay where it is. So we're going to go from 0 to 2, x over u times du over 2x. And trying to color code that so that it kind of makes it a little more apparent. Then we know the x's cancel. So we have a 1/2 1 over u du, which is 1/2 natural log of u. And then we substitute back in. So that's 1/2 natural log of the absolute value of 1 plus x squared, and then plus c. Now the absolute values there, not plus c, excuse me. The absolute values there are not really necessary because 1 plus x squared will always be positive, but it doesn't hurt to put them in. Let me erase that. We don't have the 1 plus c because we have definite integral here. We're going to evaluate that from 0 to 2. Okay, so let me actually move that to, I might need a little more space. Okay, so we have then 1/2 natural log of 5. Let's show you where that 5 comes from. 1 plus 2 squared minus 1/2 natural log of 1 plus 0 squared. Okay, so we have, and this is really common. I'll show you in just a second. This is 1/2 natural log of 5. And, once we know it's a 5, we don't need the absolute values for sure. 1/2 minus 1/2 natural log of 1. Okay, this is the important thing here. The natural log of 1 is 0. They use this all the time. Okay, and so look for those sort of things. Natural log of 1 is 0, and exponentials to e to the 0 is 1. They do those things all the time. Okay, so the answer is 1/2 natural log of the absolute value of 5, or 1/2 natural log of 5. Okay, looking at the next one. Interesting. So this next one, I'm going to think that it is completing the square. And so I'm going to do that. Oh, wait a minute. It's not a completing the square. Ooh, tricky one. This is actually a U sub. No kidding. It really is. I'm trying to decide what color I want to use here. Let's go brown. This is actually a U sub. What? Seriously is. Okay, so, you know, the tip that, you know, let U be the denominator. So we're going to let x squared plus 10x plus 26 be the denominator. And then du dx is 2x plus 10, which is twice the x plus 5. Huh, wow, that's pretty cool. So, so solving for dx, then we get du over 2x plus 10. Okay, I'm going to rewrite that. I'm going to say dx equals du over 2 times the quantity x plus 5, because that's what I want to get to cancel. That's the kind of tricky thing there. Okay, so that means the dx here, whoopsies, the dx is going to be replaced by this, and the u is going to replace this. And so we are going to have x plus 5, we're going to leave that alone, over u times du over 2x plus 5. And so if you notice that x plus 5 binomial, and I'm just going to do this, right, because this is grouped in the top and the other one's grouped in the bottom, this cancels with this. And so we have 1/2 1 over u du, which is 1/2 natural log of the absolute value of u. And the absolute value of u is that x, that trinomial x squared plus 10x plus 26. So that is 1/2 natural log the absolute value of x squared plus, oh, I've forgotten already, 10x plus 26. 10x plus 26 plus c. It's an antiderivative. Okay, number 4 looks like it's a long division. So this is a long division. We see that the top has a higher power than the bottom. So I'm going to write the top in standard form. It's going to be x squared plus 0x plus 1. And I'm going to see how many times 2x goes into it. And so if that's the case, I need a half x here. And a half x times 2x is x squared. We're going to subtract that. That's going to be 0. 0 plus 0x, which is going to go in 0 times. And then the 1's going to come down. So I can subtract that, I guess. And then we can bring the 1 down, which is smaller in power than 2x. So we have plus 1 over 2x. Okay, so this is equivalent then to 1/2 x plus 1 over 2x dx. And so integrating that, is this a definite integral? No, it's an antiderivative. Okay, so that is 1, oops, I don't need the antiderivative sign. Get rid of that. There we go. So we have 1/2 times x squared over 2. That's the antiderivative of x. And then let me just write this in one more step. 1/2 1 over x dx. That's what we really have in that step. So we have let me simplify that. That looks like x squared over 4, that first term, plus 1/2. Then 1 over x dx is just natural log of the absolute value of x. And then plus c. Okay, this next one is definitely a completing the square. You get a 1 over a non-factorable polynomial. And so let's take a look at just the denominator. Let's set up this denominator as a perfect square. So we've got r squared plus 10r, and then I need to leave some space, and then we have a plus 26 on the outside. So let's see, what do we need for a perfect square here? We need half of 10, and then we need to square it. So it's 25. We're going to add 25, so we're going to subtract 25 here. So what that means is that we have, that's a perfect square trinomial in the brackets, and that's going to be an r plus 5 quantity squared. And then this is going to be a plus 1, which is also a perfect square, if you think about that. So we have 1 over dr, and I'm going to put it as 1 squared plus r plus 5 squared. And then that way we know our a is 1 and our u is r plus 5. And so we don't have a radical, so it's got to be an inverse tan. So we know it's an inverse tan. And we need 1 over a, which is 1 over 1. And then in the brackets here, we need u over a. So it's going to be r plus 5 over 1. And this is an antiderivative, so it's going to be a plus c. We could just leave it like that. I'm just going to clean that up a little bit. That would be an inverse tan of r plus 5 and then plus c. Okay, so this one is just a straight trig rule. So if we know that when we differentiate tan, we get secant squared. So this is a, I don't know how to, tan to secant squared, vice versa. I'll do a double arrow there. This is just a, I'll call it a basic rule because it comes right out of your flip book. So this is a tan. Now we could do a u sub here, but we know it's going to be a tan x plus 3 plus c because the derivative of x plus 3 is 1. So let me just kind of set up the u sub. If I said u equals x plus 3, then du dx equals 1, which means du equals dx. So this would be a secant squared u with a straight du, because du and dx are the same thing when the derivative of that inner function of the composite is 1. And so it would just be a straight substitution. You'd get your x plus 3. You know, this would be a tan u plus c. So you could do a u sub there and then get back to that if you wanted to. But that's unnecessary if you see that equivalency there. Number 7 is also one of those where, you know, maybe I need to come back up here and we could almost call this a u sub, but you don't have to. And number 7 kind of falls into the same category. We could call this a u sub. We'll talk about that, but it really is a basic rule. With that derivative of the inside being divided out, we're kind of reversing the chain rule. That's all the u sub is. So we know that e to the whatever, its antiderivative is e to the whatever. And then with those linear expressions in the composite, we just divide by the derivative of that linear expression. We put a plus c on. Okay, so let's show you what that looks like with a u sub. So with a u sub, we'd say let u equal to negative 2t. It's important to bring that negative sign with you to get it to get that substitution to look as clean as possible. So negative 2t, then du dx is negative 2, and dx is equal to du divided by negative 2. So you can start to see why that negative 2 goes into that shortcut right there, because now this substitution is going to be e to the u, right? We're gonna substitute this in here, and we're going to substitute this in here. And let me go back and make some corrections here, because this is not a dx, it's a dt. Sorry about that, I used the wrong variable. There we go. So this is going to be an e to the u times du over negative 2. So you can see that negative 2 comes out in front in the denominator. That's where the negative half comes from. And e to the u du is just going to be e to the u. So this is the negative half e to the minus 2t, or e to the u plus c. So that's how we get back there. Maybe I should do this, because that would be consistent with the previous problem, right? That gets us back to here. So that's where that negative 2 and that's where that dividing by the derivative when it's linear works, is because that just ends up being the differential substitution. Okay, for number 8, you got to recognize number 8 is a natural log. So this is a basic rule. So, and it could be a u sub though. It could be a u sub if we wanted it to be. But we're looking at this and we see that we have a 1 over x with a constant. And so this is really the natural log of the absolute value of 25 plus x. So if we did this as a u sub, it would look like this. U equals 25 plus x. Du dx equals 1. So du is equal to dx. So it's a direct, the substitution is really straightforward then. It's going to be a 1 over a u du. And that's how we get to the natural log. This one's a definite integral. So we are going to go from negative 24 to 0. And so we're going to have natural log of 25 plus 0, absolute value, minus natural log of 25 minus 24. This is really a common thing. I'll get to it in a second. Okay, so this is natural log. This is natural log of 25. And the really common thing I'm talking about is minus natural log of 1. They love to do this. Natural log of 1, of course, is 0, but they love to incorporate that sort of stuff. So this is the natural log of 25. Now, just to give you some alternative forms of the answer, that's also the natural log of 5 squared, which means it can be written as 2 natural log of 5. So don't forget about those logarithmic properties that kind of come into play here. Number 9 is a u sub also, but it's one of those I would call a basic rule. I would still call this a basic rule. We'll do them both ways just to kind of show you, but these are I'm trying to get you comfortable with when we have that linear composite here, right? This is linear. 5t plus 1 is like 5x plus 1. When we have those linear inner functions, we should be able to do that u sub on the fly. So this would be a sine of 5t plus 1 divided by 5. Okay, remember the chain rule. This is a reversal of the chain rule. That's all a u sub is. It just breaks down the steps more. But you know, the chain rule is the differentiation part of the chain rule is multiplied by the inside, derivative of the inside. So we're reversing that. We're dividing by the derivative of the inside. So let's call this u. Let's make u 5t plus 1. Then du dt is 5, which means dt is du over 5. So you can kind of see where that 5 in the denominator comes from, right? Because when we do this substitution in, then we're going to say this is a cosine u times du divided by 5. And so that's that's why I'm saying we can just divide by the derivative of the inside, because that derivative ends up being a constant, and that constant can just slide right out of the integrand. So we have the 1/5 integral cosine u du, and of course the integral of cosine u du is sine. So that's why we can do that real quickly if you're comfortable with that. And then of course this is an antiderivative with no limits of integration, so we're going to put a plus c on the end there. All right, so number 10, we've got polynomial top bottom. We've got the degree is equal So this falls into the long division category because we have a degree in the numerator of equal or greater value. So that means we're going to see how many times x squared plus 1 goes into, this is the tricky part, we're going to write this as x squared plus 0x plus 0, because we have that one term, right, the x squared plus 1, and so we have a constant term, so we have to write that standard form all the way out to that constant term. So we got to include this because of this, so to speak. Okay, so x squared goes into x squared once. So we have x squared plus 1, and we're going to subtract that. And when we do that, we have x squared minus x squared, which is 0, 0x minus 0x, which is still 0, 0 minus 1, which is negative 1. So it was a real quick, wasn't too long of a long division. So we have then a remainder, it looks like minus 1 over x squared plus 1. So we have 1 minus 1 over x squared plus 1 dx. And that bottom, that denominator should be a kind of a little red flag that, hey, I've got a polynomial now in the denominator with just a constant in the numerator. That's got to be an inverse tan, right? No radical, so it's not an inverse sine. It's got to be an inverse tan. So that means the u equals x and the a equals 1. So when we do the antiderivative here, we've got x, and that x comes from integrating the 1. And then we've got minus 1 over a inverse tan u over a. U over a. Is this an antiderivative? Nope, it's a definite integral. Okay, so let's rewrite that. So we have x minus inverse tan of x, and we are evaluating that from 0 to 1. All right, so we have to evaluate an inverse tan with no calculator. It's not so bad, to be honest. Let me just, I'm going to take this and scooch this down here so I have some room to draw a graph. Okay, so pause the video for a second and try to draw the tangent, not the inverse tangent, but the tangent of x. Okay, if you're watching, if you started the video again, I'm assuming you've already drawn the tangent of x. I'm going to draw it pink because I'm going to use green for inverse tangent. Tangent of x looks like this, right? So that's tangent of x, and we know that we have an asymptote right here, and that asymptote is pi over 2, and we have another asymptote over here, and that's negative pi over 2. Okay, so what does inverse tan look like? Well, inverse tan is the inverse of that function. So what we want to do is we want to just basically fold that over the line y equals x. So if we can kind of picture the line y equals x here, that means the inverse tan looks like this, which means that we have a horizontal asymptote up here at pi over 2, and like this, which means we have a horizontal asymptote at negative pi over 2. Okay, so when x equals 1, then basically what it's saying is that the inverse tan is saying, well, let me plug this in. Let me do the fundamental theorem of calculus. So we're saying 1 minus inverse tan of 1 minus 0 minus inverse tan of 0. That's what we're saying here. And so the inverse tan of 1 is saying what radian measure am I at when I have a tangent of 1. So that is a really common question. And that is, in other words, where is my tangent ratio equal to 1? And that is at pi over 4. So this ends up being 1 minus pi over 4. And then where is my tangent equal to 0? And that is at a radian measure of 0. So this is minus 0. This whole thing is 0 here. So the answer then is 1 minus pi over 4, which you might see written as 4 minus pi over 4 as a single fraction like that. That's pretty common as well. Okay, let's look at 11. So 11 definitely could do a u sub here, but you don't have to. You could also apply your basic rule with because again we have this linear inner function here. So we'll do it both ways. We'll continue to do this until you get comfortable with this. We'll show you the basic, and then we'll go back and wrap around and do the u sub. Okay, so we know that e to a power, its antiderivative is e to a power. So this is going to be e to the x minus 5, and then we're going to divide by the derivative of the inside, which is 1. So that is e to the x minus 5. And then we have to evaluate that from 0 to 5 because we never changed variables. So we're evaluating that at x equals 0 and x equals 5. Okay, so that would be then plugging in 5, that's e to the 0, minus e to the negative 5, right? Maybe I need to do this. Instead of e to the 0, maybe I need to do the e to the 5 minus 5 and 0 minus 5. And so that's e to the 0 minus e to the minus 5. Now, they do this to you a lot with exponentials. A lot of people think e to the 0 is 0, and it's not. This is 1, right? Anything to the 0 power is 1. And you better bet that whatever value this is with the 0 here is going to be part of your, is going to be a teaser if it's a multiple choice. So this is 1 minus e to the minus 5 is 1 over e to the 5th. So this is another opportunity for them to give you an answer, that form that you might not recognize. And so we can think of 1 as e to the 5th over e to the 5th minus 1 over e to the 5th. So a lot of times they'll call this e to the 5th minus 1 over e to the 5th, okay, to write it as a single fraction. Okay, so let's do that u sub now. Let's say, I'll change colors for the u sub. Let's say this is your u, x minus 5. So your du dx is equal to 1. So your du is equal to your dx. It's a direct substitution. So that means we have e to the u du, and the antiderivative of e to the u du is e to the u. Now we need your limit changes. So when x equals 5, watch what happens here. U equals 5 minus 5, which is 0. That's the top. That's the top. And when x equals 0, u equals 0 minus 5. I forgot my equal sign there, which equals minus 5. That's the bottom. See how we get the negative power there? Because of the change in variables. So this is now e to the 0 minus e to the negative 5. And as you can see, we end up with the same expression, which means we have the same simplifying occurring. Okay, so number 12 is really similar to number 8. So it's a natural log. We still have a linear expression here, right? So this is a linear, a linear inner function there, and so we could, I still consider this really a basic rule, but it's also, we can also use our u sub if we're not comfortable doing the basic rule. So I'll go through this both ways. So if I recognize this as a basic rule, then I'm going to look at this as a 1 over u. and I'm going to call it a natural log of the absolute value of u, which is 7m minus 5. You see I'm kind of doing that in my head. And then divided by the derivative of that, which is 7. And then plus c. So that's the antiderivative for that. So let's follow that through with what happens when we do a u sub. So let's call this u, 7m minus 5, du dm equals 7. So dm is du over 7. That's where the 7 in the denominator comes from. So when I substitute, I get a 1 over u times du over 7, which is a 1/7 du over u. A lot of people write it like that, which is a 1 over u du. And that's how we get the natural log, right? 1 over u is natural log. 1/7 natural log of u. And then when we come back and substitute the u out, we get the 7m minus 5. So that shows you that basic rule, and then accommodating for the constant derivative of that inner part of the composite really does work out. Okay, 13, I just noticed, looks like 13, I have a typo. I think this is definitely a typo. I know that. This should be not x minus 5. I forgot to change the power on that. So let me get creative here. I'm going to, ooh, that was a bit too big. Let's do maybe that. Let's get rid of that. And then let's call it minus 2x. That's what I meant for it to be, minus 2x. Okay, so again, this is it's a basic e to the x, also u sub though, so we will go through it both ways, just in case you want to see it both ways. Okay, so we know that integrating e to a power is itself, so we know this is e to the minus 2x divided by minus 2. And then we're going to evaluate that from 0 to 3. So when we stick in 3, we get e to the minus 6 over negative 2. When we stick in 0, we get e to the 0 over negative 2. Well, over negative 2, yeah, because the minus comes from the fundamental theorem and the negative 2 is in the denominator. Be really super careful. Here's another one of those e to the zeros, right? That does not equal 0, it equals 1. So, you know, that's really common. They love to do that, and they love to trick you with really convincing teaser answers. So this is e to the 6 over negative 2 minus e to the 0 over negative 2. And we have common denominators there. So that is negative 2 in the denominator, and then I have e to the minus 6 minus e to the 0. Let's stop calling that e to the 0 though. Let's call that 1 already. Minus 1. There we go. And what they might do here, because the negative 2 in the denominator is really kind of weird, what they might do is they might do this. Negative 1 over negative 2 is positive a half, so the 1, and then e to the negative 6 over negative 2 is really negative, so they might do this. And then they can put it over a positive 2. So that might be an alternative answer form. Okay, so let's do the u sub here. So we know that power is a location of a grouping location. So u is minus 2x. So du dx is minus 2. And so dx ends up being du over 2, right? That's where, over minus 2, excuse me. Almost dropped the minus sign there. That's where this minus 2 comes from, if you do it using your basic rules. So we are integrating then e to the u times du over negative 2, which is the same thing as saying negative 1/2 e to the u du, which gets us what you see that we came up with using the basic rules. Okay, so these last two fall into the same category. They're both U subs. So U subs are, if you haven't gathered right now, U subs are super, super popular, right? So this is a U sub because I see a function and its derivative. This is the derivative because it's 1 over t squared. So in other words, in my brain, I'm thinking of it like this: 1 over t squared times secant 1 over t tan 1 over t dt. That's how I'm thinking about it. And so this is the 1 over t squared is the derivative. Okay, so we'll let u equal 1 over t. That's t to the minus 1. Right, that's how we need to think about it to do the power rule. Okay, differentiating du dt equals minus 1 t to the minus 2. So that equals minus 1 over t squared. So the only thing we don't have is the minus 1. So that means dt equals, how about this? Minus dt equals t squared du. And then that means dt equals minus t squared du. Oops, that should be a du. Okay, so my substitution then looks like this. I'm leaving the 1 over t squared alone. It's going to be secant u tan u times, I need brackets here because I got a minus sign, times a negative t squared du. So if you notice, we have a negative because of that bringing down of the negative 1, that power rule. Okay, so now my t squares cancel. My negative, I'm going to bring my negative out front. So we are going to have negative secant u tan u du. So now it's a basic rule, and that basic rule is the antiderivative of secant u tan u is tan u. No, I said that wrong. It's secant u, my bad. So this is negative secant u plus c, and then we can substitute back in. It's minus secant u, get the u out of there, secant 1 over t plus c. Okay, so this last one is also u sub, and it just piggybacks right off of what we did here. So this is also a u sub, and we're going to think of it as the antiderivative of 1 over the square root of w times cosecant squared of the square root of w dw. So our u is going to be the square root of w, which we are going to think about as w to the half power so that we can do the power rule. So du dx then equals 1/2 w to the minus 1/2. So du dx equals 1 over 2 square root w. I'm writing it that way so that it matches up with what I see in my integrand. So I'm going to cross multiply here. I get 2 root w du equals dx. That's my substitution. So my substitution then is going to look like this. I'm going to keep the 1 over the square root of w. This is going to be cosecant squared of u times 2 square root of w dx. You can see how these get too complicated to try to do a shortcut here, a basic rule shortcut. So looks like my square roots of w cancel out, and then I have 2, I'm going to factor out the 2 cosecant squared u du. Sorry, I have a error right here. It shouldn't be a dx, it should be a du. There we go. And the antiderivative, now this might be a bit of a stretch, but think about it. If it were a secant squared, the antiderivative would be tan. This is a cosecant squared, so the antiderivative is cotan. So this is a 2 cotan u plus c, and then we're going to put our u back in. Our u, if you remember, is the square root of w. Yep. So this is 2 cotangent root W plus C.